Okay. So first, I'm going to start off by doing, and it'll take about 5 minutes to do what we sort of ended with last time, just because it's a nice, simple little thing, so we can all see what the point was for most of these regularity things that we're doing before, and then we'll move on to some other stuff. So the theorem that one gets on this epsilon regularity very, very quickly is the following. So let's assume we just write about that. You have to be a Mills connection. On, as always, say that ball radius 2, I don't really care. Sorry, A, I don't really care again. Do some clear to that. Land or whatever. Then let's define what we're going to call a bad set. So let's call maybe the R bad set if you want. R bad. With a set of points, let's say the ball of radius 1, such that the regularity scale is less than R. So let's make a few little comments about that, right? So note, right, that I mean, this is a set of points, for instance, for which the curvature's got to be at least R to the minus 2, roughly speaking, right? So that's the. Oops. Okay. So this is a set of points for which the curvature is at least R to the minus 2, for instance. But it's somehow much better than this, because this is the set of points where even if the curvature happened to be really, really well behaved, it can't even be close. I mean, if a point's not in this set, then it can't even be close to a point with large curvature. Right? So that's somehow the point. So we already know that just because the curvature is in L2, that most points have some reasonable amount of curvature. This set here is about studying those points which have reasonable curvature and are not close to other points that don't have reasonable curvature. So it's a much stronger notion of regularity. So let that be the bad set. Then one can prove this codimension 4 regularity estimate. So namely the volume of the bad set of radius R is less than or equal to some constants, depending on n and k, times our total energy, times r to the 4th. This here is really a statement here. I mean, so the way you should be thinking for a second, imagine your singular set or your bad set, if you want, was just a nice manifold sitting inside of it, just for argument's sake. What is an R tubular neighborhood of? I mean, I could stick an R tubular neighborhood in here with no trouble, just to get intuition. Well, what's an R tubular neighborhood of some n-4 dimensional manifold? Which its volume it behaves like a 4th, right? So this is telling you that your bad set has a codimension 4. It's a very nice sense. So most points in a codimension 4 sense don't just look. I mean, they aren't just smooth points, but there's some definite amount of smoothness. They aren't just have bounded curvature, but they're not even close to points that don't have bounded curvature. So how does one prove this, given the epsilon regularity from before? So in fact, it's quite simple. So first, let's just note the following. So if x is a bad point, then what can we say about x? Well, our epsilon regularity theorem from before tells us that if we look at some definite size ball around it relative to r, then the curvature has to have some definite size on it. So more precisely, right? So our if we look at a ball of radius r naught inverse, that was just depending on n and k from our epsilon regularity from before, to the 4 minus n times the integral over the ball of radius r naught r of x of the curvature squared. Then this had some definite size to it. That was what our epsilon regularity theorem before, because we claimed if this was less than epsilon, then the regularity scale had to be less than or equal to r, or r naught times the radius, which is r. Right? So every one of these points has a lot of L2 curvature ahead of it. That's why we like epsilon regularity theorems involving L2 curvature, not pointwise curvature. This is something which we can now try to control with that. So what's the standard trick at this point? So let's note the following. So we look at the bad set. Well, if I'm trying to control its volume, or let's even say the volume of the ball of radius r around that if you want. So let's just look at a covering of this thing, right? I mean, this thing is inside the union of every ball of radius r naught r of x. X is inside the bad set. So in fact, the whole ball of radius r is inside this set. Obviously, it's much better, right? I'm basically looking at the ball of radius r naught inverse by definition. This is kind of a dumb statement almost, right? But now what you do is you play the usual Vitali covering tricks, right? So there is some sub-collection of this thing, right? We can put that inside a union of balls of radius, let's just say, I think for constant you could actually go to 2, but I'm going to say 5. Of xi, where xi is in the bad set, such that the balls of radius this over 5, which is just those balls, are disjoint. Right, so this is the standard Vitali covering. If you're not familiar with Vitali coverings, you must Google this tonight and you must work 15 examples. Now, there is no subject being talked about in these last 2 weeks that doesn't use this constantly, right, intuitively. The proof's very simple, right? Basically, you just take a maximal disjoint. I mean, just look at, any collection of this for which these guys are disjoint, a maximal, meaning you can't stick another ball the same size with the center in the bad set such that it's still disjoint. Check that 5 times that radius covers the whole thing, otherwise you have a contradiction of being maximal, right? So it is a very easy proof. But now why is that good, right? So that means that if we can cover this by this, well, how many sets are in here? I don't know. There's some n number of these balls, whatever that is. So then the volume of the ball of radius r around the bad set is going to be less than or equal to the number of balls times the volume of these balls. So less than or equal to n times the volume of those balls, and this is just some constants times r to the n. Right? Each one of these volumes has volume r naught inverse to the times r to the power of n, and I just shoved the r naught inverse inside some constant. I don't care. So what we have to do then to estimate the volume of this is estimate the number of these balls. Right? That becomes our goal now. And let's see, this is a one-liner. Let me keep this note up. Well, if I want to cover these, what are we going to do? Well, let's just see what happens now. So we know this actually holds for every one of these balls. So let's use this. So we have that lambda here is equal to the integral over the ball of radius 2 of the curvature squared. Inside our collection of xi, the balls of radius r naught inverse times r disjoint. So that means whatever this is, it's bigger than or equal to the sum over all these balls of the curvature squared over those balls. But now what do we know? We know that each one of these satisfies a certain estimate, right? So this is bigger than or equal to the number of balls times our lower bound on each of these guys. So the lower bound on each of these guys is some, well, epsilon of nk times another nk constant, which I'm going to call another nk constant, and just absorb everything together, times r to the n minus 4. Okay, but now we just move things over, right? What's that tell us? This tells us that n is bounded by some constant. We're analysts, right? So in every single line, constants mean something new. Constant times lambda times r to the 4 minus n. And if we plug that in up there, we're done. We get our 4. It would be an excellent exercise to do this from the beginning, right? This is the type of trick that gets used constantly and continuously. One should be, like breathing. Good? Confusion should be addressed now because I am utterly changing topics from this point forward. Like starting all over from it. Okay? Good deal. Okay, so the rest of today's lecture is going to be a little bit on the more advanced level. So we'll start off with basically some overview of a bunch of things we haven't gotten to. We basically need more time to get to, and we'll just see some examples of how they all work. We'll state some basic structure theorems about singular sets in higher dimensions of Yang-Mills, and we're going to try to understand the energy identity a little bit. That there's some sort of conjectural picture about how things blow up. And with whatever time is left over, we will sketch the proof as being probably optimistic. We'll sketch some of the points of the proof. So, most of actually, the stuff I'll be talking about is joint with Valtorta, so I thought I should mention that right in the beginning. The focus, by the way, I'm taking a lot of these lecture notes from some colloquiums and seminars I gave, so if the wording sounds weird for summer school, that's why. Let me give you a little bit of a spiel about what we're going to be studying. So we're going to be studying something called defect measures coming up. So the general idea is something that is extremely common in lots of nonlinear PDEs, right? So that this is just, as with many of our topics, it is a general phenomenon that occurs. So oftentimes, when you're studying nonlinear PDEs, you are in fact not interested in a single solution. You are interested in a sequence of solutions. Reasons for this can include a few different points. One, you might just be compactifying some moduli space. This is sort of a common thing for Yang-Mills and other points. So that is, you're trying to take limits of solutions and throw those into some bigger space. Much more basic is that you just may be trying to prove something by contradiction. For nonlinear PDEs, that is an extremely common proof technique to prove stuff by contradiction. And so if you have a sequence of solutions, then even if by some miracle, whatever, these solutions all happen to be smooth, which of course in principle won't happen, but let's even just say it is, what they won't be is uniformly smooth. Something's blowing up, something's going wrong in this sequence, and what we want to understand is what goes wrong and how it goes wrong. So where is blow-up occurring? How much a blow-up is occurring? Well, can this blow up arbitrarily? If it could blow up arbitrarily, then in some sense this whole business is doomed. And the answer, of course, is no, it can't blow up arbitrarily. So how do we understand where the blow-up occurs, what it looks like, and how to compute it? And there's this wonderful object for this called the defect measure. It's an actual measure that you basically associate to this sequence, which we'll write down today. And there are these nice sort of conjectural pictures about what the defect measure is supposed to be. This is what the energy identity is. The energy identity basically predicts that this defect measure, besides having a nice structure, in fact, if you wanted to actually look at a given point of it and understand exactly how much energy is sort of associated to that defect measure at that point, you should be able to compute this. And so let me use a bunch of big words now, and we'll be spending a lot of time understanding these words. So the result for the energy identity is to say that the energy density of this defect measure coming from a sequence of Yang-Mills can be computed explicitly as the sum of bubble energies, right? So a bunch of words, and we'll hit all those words before we're done. The second thing we'll kind of talk about a little bit, which turns out to be quite related, is a certain estimate for stationary Yang-Mills. So when you're in linear PDEs, what are the basic theorems? The basic theorems are all about a priori estimates. Right? You have a solution of a harmonic function or something like that. You have some energy bound on a ball, and a ball of half that size. You want to have bounds of higher order objects, right? And for nonlinear PDEs, it's really the same. You want to prove things like this. Of course, you don't expect bounds of infinite orders. The sharp sort of conjectural bound for stationary Yang-Mills is that they're supposed to have an L1 bound on the Hessian of the curvature. That's supposed to be somehow the best one might hope for as being true. And our second result is basically to say that this is true. We'll actually explain why these two things are so related before we're done. And it'll sort of make clear why this was conjectured in the first place. An interesting point, which won't matter to anybody here, but I'm going to make a statement about it real quick, is that those two are actually proved in tandem. So you kind of actually have to prove both results at the same time. An expert would be surprised by that. Okay, so basic outline of what we're going to do for the rest of today. We're going to do a whole bunch of preliminaries, which will be very shortened because we've had 2 full days of preliminaries at this point. What we haven't done preliminaries on at this point, which we will do today, are things like limits, regularity in higher dimensions, defect measures, so forth and so on. That'll be our main focus of preliminaries for today. Some background on various literature in the subject, and we'll talk about the results. And with whatever time we have, it'd be nice to outline the proof techniques of these results because they're kind of useful anyway. I'll give examples how these same techniques can be used to sort of prove other theorems as well. So it's sort of useful information. The basic outline will kind of go as follows. And let me again, basically, for the rest of this slide, I'm going to throw more big words at you that we'll eventually come back to. My experience is that for most of these things, it's only about the 8th time you hear the word it starts to make sense. So I just want to say it a whole bunch of times. So if we can get to like the 4th time by the end of the talk, I'll be happy. All right. So mainly we'll prove things by example. So basically I'm going to stick the simplest possible example in front of you. We'll see it's true there, and we'll call ourselves pretty happy if we understand that. Really, of course, the example is the motivation for why people conjecture this in the first place, not really a proof outline, but, you know, we take what we can get. So one point we'll discuss here is something called the quantitative bubble tree decomposition. Roughly speaking, well, what I'll try to show you how to do to, some rough extent or another, especially in some examples, is that you want to take an arbitrary solution, say a stationary Yang-Mills or a nonlinear harmonic map or an Einstein manifold, whatever. You can use in quite a few contexts. And you basically want to decompose it into pieces, right? These pieces have this structure, these pieces have that structure. And the important ingredient here is that, you need to bound the number of pieces, and you want those pieces themselves to have as much structure that you can get away with while still bounding the number of pieces that actually appear in this decomposition. And then what you hope to do is prove everything you want to prove on each piece individually and just kind of put it together in one big package at the end to get a theorem. The 2 pieces that will appear are called, in this particular decomposition, decomposing things into balls is basically analysis, right? That this is, half of analysis is about finding out the right way of decomposing things into balls. Here, the 2 pieces are called quantitative bubble regions and quantitative annular regions. And most of our time today will be focused on the quantitative annular regions. They are on the one hand somehow the simplest piece, but they are on the other hand the hardest piece. Simplest to kind of, they look the simplest, if, from a naive point of view, but it turns out the analysis on them is the hardest. And an expert would understand this as being sort of what was lacking in proving any of this stuff before, any sort of analysis on this guy. Doing analysis on this will take a couple of points. I'm going to show you kind of a new gauge condition today, which we call an epsilon gauge. We call it an epsilon gauge because it's not really a gauge. Our main problem here was that one wants to do analysis over singular sets. So we'll discuss this again, right? But all these nice Coulomb gauges, which are awesome, they kind of only exist and are useful on regions where curvature is small. In some sense or another, if you're over a singular set, they either don't exist, or if they exist, they're pretty horrible and not very useful. One really needs a way of actually working on singular sets. So these gauges turn out to be much more adaptable to this. And then again, just to use an annoying word, the main way we estimate those gauges is through a certain log superconvexity. One of your homework assignments gives you a very basic baby case of this for harmonic maps. Okay, background, notation. As always, we're talking about a ball and a Riemannian manifold, and as always, this is just Euclidean space, I don't care. For our discussions, we're always going to work on the trivial vector bundle over a ball. But let me just point out real quick, even though I'll try to avoid it from this point forward, this is really all done for principal bundles. Connections on, Yang-Mills is really about connections on principal bundles and that sort of thing, not vector bundles themselves necessarily. They're obviously closely related. But all these results really hold for principal bundles. A is going to be our connection on our vector bundle from our point of view, and its curvature is going to, its energy functional is the one we've been discussing, the Yang-Mills energy functional. Right? So hopefully we're kind of happy with all of these things at this point. Couple points. and it solves these equations, right? So this is what we spent the last couple of days talking about. We've got our Bianchi identity, we've got our Lagrange equation, we've got our stationary equation. And as we've been doing, I'll use E to denote the vector bundle that this thing induces. So in fact, even in practice, when you're working on the principal bundles, you can always associate the principal bundles, vector bundles, through representations, right? And in fact, we actually want to work on the vector bundle anyway, so there's really no harm in just thinking about vector bundles. That's where the epsilon gauges live. In fact, they don't live on the principal bundle. And that's actually a major difference in terms of gauges and these epsilon gauges. Okay. Crash course on regularity. So the first part of this is sort of what we've been discussing the last day, but let me remind you. And the second part's kind of what higher dimensional versions of this look like. I'll be a little vague on statements. I'm aiming more for intuition than I am for rigor here. Again, the goal being the 8th time it'll be more familiar. So this solves some sort of nonlinear equation, of course, and therefore it's not smooth. And we want to ask questions about, how, is it smooth in some regions? That basically says yes, right? How big of a region is it smooth on? That says away from a codimension 4 region. If it has singular sets, what do those look like, right? This is sort of what we want to kind of understand a little bit. What we basically just prove here, right, is that it's effectively smooth away from an n-4 dimensional set E. That is, I didn't quite actually build an E, different E than the last E. I didn't quite build, an actual set that this thing is, smooth away from, but one can kind of imagine in this picture as being the bad 0 set or something. It's actually a little bigger than that, but that's fine. So that, roughly speaking, you view this bad set as being an n-4 rectifiable, and for the sake of our conversations, if you don't like that word, it means n-4 manifold. Slightly closer to realistic is that n-4 rectifiable means an n-4 manifold away from a set of measure 0. Where this gets bad is that the measure 0 set doesn't need to be closed, right? So there's no topology being associated. You're just throwing some measure 0 set out of a manifold. And what you can prove is that there's this sort of n-4 manifold set E such that the curvature is bounded away from it in this sort of scale invariant sense, right? So you are actually bounded on most of your you're smoothly bounded on most of your space if you have a Yang-Mills connection. And oops, right. And the subtle point to this sort of n-4 estimates we just discussed. So this here, it proves things don't blow up except on maybe an n-4 dimensional set. Things can blow up on an n-4 dimensional set. One of your homework problems gave an example of this, but we will work through it today. But despite this, you are generally actually smooth on a larger set, but you just don't know how smooth. So one knows that you're smooth away from an n-4 measure 0 set. And one of the really nice conjectures left over here is that you're actually smooth away from a codimension 5 set in general. Right? As a nice clear example, that means in dimension 4, Yang-Mills are always smooth, but not effectively so. Well, we'll see exactly how this happens. That's basically what defect measure quantifies. Okay. So as sort of a continued crash course in our regularity theory. So now these next points we haven't discussed yet, right? So that was more of a review. So what's a consequence in dimension 4? Of this point. So imagine now we want to study a sequence of connections on, again, just the ball of radius 2, whatever, uniformly bounded energy, whatever. Then what this estimate here actually allows you to do is to take a subsequence. Now, codimension 4 here actually basically means isolated finite number of points, right? So it means that you can take a subsequence that will converge away from a finite number of points, converge smoothly away from a finite number of points to some connection in the limit. As it turns out, that limit connection A will itself be smooth. So that these AIs, they'll converge smoothly away from some points to some smooth connection A, as it turns out, which is also Yang-Mills, but the convergence is only smooth away from some points, right? So something weird is happening here, right? Smooth things converging to a smooth thing, but not smoothly. In higher dimensions, something like this kind of happens as well. So you can still take a sequence of connections AI they're still going to converge smoothly away from some codimension 4 set. That basically means more like an n-4 manifold set now, so not isolated points. But what they converge to, the A they converge to now may actually have singular sets in higher dimensions. So you don't have to be smooth this length. But you will be smooth away from an n-4 measure 0 set or conjecturally n-5 set. So A is still pretty nice, even though it's not necessarily smooth. It's not clear that A, in fact, I doubt it is, actually Yang-Mills in higher dimensions, though. This doesn't always have to be true. Stationary Yang-Mills. It will be weakly Yang-Mills. This is one way in which this distinction between stationary and weakly actually kind of plays a role. I don't think anyone's actually built an example for Yang-Mills, but they have for harmonic maps, and my guess is that the same constructions work. Nice problem, by the way, if anyone wants to Google it and go work on it. Structure theory. So imagine now we have some sort of stationary harmonic map, and we're not going to really use any of this, by the way, for the rest of this lecture. I'm telling you this just because I think you should see it once, but we'll kind of move past it. So however lost you feel at the end of the slide, it's okay. Imagine you have a stationary connection A, or imagine A is a limit of stationary connections. Either one's fine. Then the way you study singular sets, and this is Yang-Mills, this is minimal surface, this is nonlinear harmonic maps or Einstein manifolds, whatever, is that it is more appropriate to actually stratify the singular sets. This is how one wants to actually build it. That is, not all singularities are created equal. Some points are more singular than other points. And you really want to split points up based on which points, how many singularities they actually have at this point. Roughly speaking, your kth stratum inside your singular set here are the set of points so that the number of the dimension of the singularities at some point is not k plus 1 dimensional. Therefore, you expect this thing to be k dimensional, your k stratum, when you look at this. We'll see some examples of this before we're done, so we can get a little bit of a feel. One wants to picture, I mean, your singular set here, so sort of, as a stratified manifold, or as, as a variety of some sort, right? So it's got some n-4 manifold part plus some n-3 manifold part that's connected to it, maybe with some corners, and an n-2 manifold that's sort of pasted in there, right? So this is how one wants to picture these. So that is to say, singular sets should be well behaved, right? They shouldn't be arbitrary and scattered all over the place. They should have some nice structure to them. A classical theorem, I think this goes back to Uhlenbeck, is that the dimension of the singular set is less than or equal to k. It is worth mentioning that the key word you want to know here is Federer dimension reduction, right? So these types of theorems, where you prove that the k stratum singular sets have dimension bounds that you expect, Hausdorff dimension bounds that you expect, first go to Federer in the minimal surface context. Right? It's all about having monotone quantities and stationary equations. This is what it kind of all comes down to. However, basically, I mean, for in the minimal surface case for 40 years, or in this case, maybe about 25 years or so, nothing else has been really understood except dimension bound on this. It's pretty bad. Last year, it was at least proved that these things are actually k-rectifiable. So that is, they are k-manifold. Basically away from a set of measure 0. So one can actually prove this. That was proved by my student, Yu Wang. And again, right, roughly k-rectifiable means it's a k-manifold away from a set of measure 0. So once again, just to be clear, I won't use any of this today. I actually don't care about stratification for the energy identity. I just thought it should be presented once. Okay, concrete examples. This was your homework, but I'm doing it anyway. Well, no, I'm not. Your homework was basically to prove what I'll say here, right? But we'll go through it real quick. So consider the manifold, which is just R4, right? With the trivial vector bundle, which is R4 across C2. So our usual sort of trivial everything. And now I want to consider some 3 elements of these are basically, 2 by 2 complex matrices, right? Endomorphisms of C2. I, J, and K, defined by this, right? So one should sort of recognize these things as being a basis for a little SU2, right? So these things are actually, they have really nice little bracket structures associated with them. This is where kind of hyperkähler structures come from and whatnot. So these aren't random is the point. And along with these sort of I mean, I want to view this as sections of the endomorphism bundle above this, right? They're constant sections, right? So these are constants, but I'm sort of viewing this, right, as saying at every point in R4, I'm associating that guy to it, right, the I, J, and K. So there are three sections of this endomorphism bundle. And I want to define three one forms, standard one forms in R4 by that complicated-looking formula there, right? There's a nice explicit thing for you. And if you do that, then we can define a connection this way. Right? Just theta 1 times I plus theta 2 times j plus theta 3 times k. Right? Divided by 1 over 1 plus the norm of x squared. One doesn't need to have an intuition for this the first time you see it. It's a mess, right? But basically, I want you to believe there are actually Yang-Mills connections in the world, right? But we should write them down. Otherwise, this has been a whole full waste of time, right? And the thing I really want you to take away from this, because I will use this later, is let's observe something interesting about the curvature of this guy. So we've got this global Yang-Mills connection on R4. The curvature is decaying polynomially at a pretty quick rate, right? So it's decaying at infinity at what is, essentially a 1 over x to the 4th rate. It's actually going pretty quick to 0 at infinity. Right? So this is the main thing I want you to take away from this, because we'll use this. Okay, so that's an example of a fixed Yang-Mills connection on R4. What I really want from this example, actually, is to build an example of a sequence of connections now. And this is what I really want. So I'm going to use this one example to build a sequence of examples. I'm going to need Blackboard space. Okay, so let's start with basically start with any finite energy connection on that should be R4 cross RK, right from our point of view. We now know one exists, right? But really, what I'm going to do will hold for any of them. There's actually a whole bunch of them, right? Take any finite energy connection on that. And as we saw in the last example, but it actually turns out to always be true, is that the curvature is going to decay polynomially at infinity. Right? That this is actually always true if you have a finite energy connection. Now, what I want to do to actually build a new example is the fun. So let's actually draw a picture real quick. So let's say this is. Here's our R4, and let's basically just graph here how the curvature is kind of behaving at the norm of the curvature as a function, right? So if here's the origin, then we're kind of having something like this, right? So the way you should be imagining this is, most of the curvature is kind of contained in the ball of radius 1, give or take, and as you go off to infinity, it's dropping very quickly, the curvature concentration of this thing. Now, do the following. I want to consider a dilation map. So for some radius r, let's just consider the mapping, which takes x and maps it to r times x, right? So as written, I'm mapping the ball of radius 1 to the ball of radius r, right? I'm just scaling in, right? And what I really want to do is do the opposite, right? I want to take the ball of radius r and pull it back to the ball of radius 1. That's what this thing is. And I want to pull this connection back by it. Oops, other way around. I want to map r inverse to the ball of radius 1, and I want to pull back the connection by that. So if AR is the pullback connection, it's a nice exercise that it's actually still Yang-Mills. That should not be completely obvious. The key word you want to know here is conformal. Dilation maps in R4 are conformal maps. Turns out Yang-Mills are preserved by conformal isometries, conformal mappings. So that's why when you pull back by dilation, you're still Yang-Mills. I can't do anything I want and still be Yang-Mills. It just so happens here that you are. So what happens when I actually pull back AR now to get a new Yang-Mills connection? If you want to do the exercise, there are two main points. One of which you can just kind of believe me for, and the other of which is a little subtle and very, very important. So the curvature itself behaves like this nonsense, but all that's really saying is that AR, its curvature, instead of being roughly supported in the ball of radius 1, it's now roughly supported in the ball of radius r. right? So I've pulled back my connection so that now most of our curvature was here, and now most of our curvature is here after I pull it back. So we've got this little spike of curvature going on. And what's particularly interesting is that after I do this, not only is the energy of this connection still bounded, it's actually exactly the same, right? Nothing changed. So here's our FA. Here's our norm of FAR. And as it turns out, their global energies on R4 are the same. In dimension 4 only, because what's happening here, so this is a great exercise to check this, and roughly what you should be viewing here when you do this pullback, right, is that the curvature itself you kind of view as being multiplied by r to the minus 4 when you do this pullback. It's getting a lot bigger, but in some sense your volume form is also getting multiplied by the exact same opposite factor, right, r to the 4th. So the two balance out. The pullback as a measure doesn't change, right, the total integral. If you were in higher dimensions, that would not happen. But in dimension 4, they have precisely the same energy. Now let's ask the question of what happens then as we let r go to 0, right? So if we fix ourselves, out here, as r keeps getting smaller and smaller and smaller, if we focus away from the origin, the curvature is going to 0. And what we kind of see then, curvature going to 0, right, is like having a function whose gradient is going to 0. A limit of such a thing would be a constant function, right? Away from that, here, constant connection means trivial connection, right? So certainly we have smooth bounds away from the origin, and it limits to something. That something will be flat. It'll have no curvature, because all the curvature is 0 outside of here, right? So our ARs converge to some A naught, which is actually just a trivial connection. So, it's 0 in our coordinates, if you want. It's flat connection. However, what we clearly see from this picture is that our sequence of smooth connections, AR, they're converging to a smooth connection, A naught. A naught's trivial, it's certainly smooth. It's not converging smoothly, right? At the origin here, we see there's definitely blow up going on. Right, so we've got a sequence of smooth things going to a smooth thing, but not smoothly. What's next? So let's now imagine we want to understand how that blow up occurs. We see it in this picture, but let's say we somehow want to keep that information that we've lost in that limit. What's one big difference between these connections? Right, these guys for any r have the same energy. This guy does not, right? Something's been lost in that limit, so we can see clearly what that something is. Because the curvature here has some size, and then it's 0 out here. And an interesting point here is that to understand this, what you shouldn't do is view the curvature as a function. You should view the curvature squared as a measure. So let's look at the energy measures of these guys. Right? So we've got a sequence of measures, but they all have the same integral, right? And what's nice about measures is that measures limit to measures, but don't drop, right? If you have a sequence of probability measures that are nicely compactly supported or something like that, decay, then they will limit to a probability measure, right? You won't lose that information. So one wants to ask, what do you limit to? And what we're clearly limiting to in the example is a Dirac delta at 0. In fact, to be more exact, we're limiting, what's the value of that Dirac delta? It's the energy of the original connection, because everything else got lost. It turns out this is your first example of a defect measure. In fact, the way I really want to write this is a 0 plus this thing. So this is an example of a defect measure. I'll give you a more general definition in a second. It's a definition / theorem, but even so. Okay. So what do we see about this defect measure? Note, first off, it's supported on a codimension 4 set. a point, right? I mean, blow up should only occur on a codimension 4 set. Therefore, the support of this defect measure, which is where blow up occurs, should itself be supported on a codimension 4 set, which just means a point here and just the origin. Okay. So let's move on to sort of understand the defect measure and slightly, with the example in mind, right? So imagine now our general case is just that we have some sequence of Yang-Mills connections. And in principle, when I say a sequence of Yang-Mills connections, I mean with uniformly bounded energy. So as before, right now we have smooth bounds on this thing away from a codimension 4 set, so we can converge them out to something. Some connection A smoothly away from some codimension 4 set. So we do so. So now we want to understand blow up of the sequence, right? So what you're going to do is much what we just did here. Let's take the sequence and let's look at their energy measures, right? And then when those limit out, right, like with, they'll limit to some measure, right? All measures will limit to some measure. And like all measures, right, we've got a nice decomposition theorem that says that there's going to be an absolutely continuous part and a non-absolutely continuous part, right? So this is, a definition half theorem here, right? Because one really needs to prove this. The absolutely continuous part will actually just be the energy measure of the limit connection. That's true, right? Hence why I wanted to write our 0 here, right? The limit connection here had 0 curvature, so it was 0, right? So in general, what it'll limit to, the absolute continuous part, will be just the curvature of the limit, plus something else, which is not absolutely continuous, and that's what we call the defect measure. So in principle, all mu here is wherever this energy disappears in the limit, right? And that's what we're measuring. And sort of clearly, right, understanding this defect measure is telling us about how singularities form. Because they're telling us about where the blow-up is occurring, how much blow-up actually occurred, the structure of this blow-up, and so forth and so on. So one really wants to understand what do these defect measures look like. Right? They're telling us everything we want to know about what went bad in that sequence. So the first structure theorem I want to state for this goes to Tian. And what you prove is the following. So you prove that the measure mu turns out to be an n-4 rectifiable measure over some s. Right? So roughly speaking, what that means is the following. So remember, n-4 rectifiable means like n-4 manifold. Just think that away from measure 0. So it's basically saying that mu here, there's some s here, which is like an n-4 manifold, and that your mu is just integration of some function along that, right? Some e of x. So, in our example over here, our n-4 rectifiable guy was just a point, right? That's certainly n-4 rectifiable. In principle, the idea is that in higher dimensions, well, it might be one dimension. If a sequence of 5-dimensional things, you might get a one-dimensional object, but it's not totally crazy object. It is going to be one rectifiable. So you can sort of think of it as being kind of like a manifold or a union of manifolds or something to this effect. This E of x here is what we call the energy density, because this is basically telling us exactly how much energy got lost at that point. How much of your curvature at that point disappeared. All right, so this guy here is the energy density. Okay. And now the energy identity is going to be the following. It'll still take us a few minutes before we can actually state it precisely. But it turns out right now that we know the support of this thing is somewhat reasonably well behaved. What one would like to ask is, how is this behaved? Is E of x basically some arbitrary function on your n-4 manifold? And the answer is basically no, and that there's sort of basically a conjectural way of explicitly computing it, right? Explicitly, knowing exactly what this thing is at some point, all right? And this is what the energy of the identity will be. But to explain that, I have to explain something called bubbles first. Again, a phenomenon that appears a lot, so it's worth knowing. Is that my next? Yes, that is my next slide. Excellent. Okay. I'm going to start off with some definitions, and we'll work our way back to an example afterwards. So let me first describe something called a bubble solution, right? So I don't think of this as being associated to anything. It's just going to be some solution of Yang-Mills with some special properties, and therefore we'll call it a bubble solution. A bubble solution, B, I'll call this to distinguish from A, Yang-Mills connection, is a smooth, I assume smooth here, Yang-Mills connection on Rn, cross E, cross Rk is fine, which is invariant under translation with respect to some n-4 dimensional subspace. So let me explain what that means. So for starters, in dimension 4, right, like over here, every solution on R4 is a bubble solution, period. If it is a solution on all of R4, it is a bubble solution, right? Now, how can, so those are bubble solutions. Now, how can you use a four-dimensional example like that to get an example in Rn? Well, just view this connection on R4 as being a connection on Rn by ignoring the last n-4 variables, right? Just pretend like they're not there. You now get a connection on Rn. That's invariant under those n-4 directions, right? So that's a bubble solution. And in fact, that's it. That's all that happens, right? So all a bubble solution is a four-dimensional solution viewed as a solution on Rn by forgetting some n-4 variables. And this subspace is just telling you what n-4 variables to forget, right? It may not be the last four, maybe last n-4, maybe it's the first n-4, just some random plane, right? But that's it. So bubble solutions are four-dimensional solutions. Let me motivate this by saying that these are, in some sense, the simplest possible solutions out there, right? So there are, and I think I write down at some points, so one can call this an exercise. It's a good exercise, which you can do now. You've got enough tools to do it. There are no finite energy solutions on R3 or R2, right? You can prove that. I mean, it has to be trivial is what I mean. So if you have a Yang-Mills solution on R2 or R3 and it's global of finite energy, it's just flat, right? Hint, monotone quantity, right? Use this and just see how things scale, right? You're going to have a problem. So dimension 4 is the first time you see something non-trivial happening. Bubble solutions are basically the simplest possible solutions out there. Now, I don't care about bubble solutions even. I want to look at what I'm going to call bubbles associated to some point. So imagine I have my sequence of connections. Imagine they've limited out and I've got some defect measure mu, like here. Imagine I take some point x on my defect measure. Then I say a bubble solution B is a bubble at x at this point here if the following happens. If there's a sequence of points going to x, I'm just going to call it x in the picture, and a sequence of radii going to 0, such that if I took my, so here's my AI going to A here, right? If I took my AIs and I got new connections by blowing them up, right? So I just want to rescale the ball of radius Ri to the ball of radius 1 and limit them out, and what they converge to is B. I call that a bubble solution. One needs an example before this kind of becomes intuitive. So we're saying, take these radii, for each I, blow that up to a ball of radius 1, maybe shift that over to the origin, pull the connection back, and if the sequence of connections you now on our balls here converges to what happens to be a bubble solution, so a four-dimensional solution really, then we call it a bubble at that point. It should, by the way, at this point, not at all be clear bubbles exist, right? Because they exist in general, right? The whole point is they will exist, and they'll exist in plenty, as it turns out. That's why we care. Another way to think about this is that what you're kind of saying here is that this solution here is disappearing in the limit here at this point. Because when you're looking at these smaller and smaller balls, this is what your solution looks like, right? And in the limit, it just goes away and disappears, right? So you're kind of looking at what vanishes as you reach your limit. So these are bubbles. Okay. Let's do an example. So recall, right? So let's take our connection A just from our original example over here, right? Maybe the explicit one we wrote down or some other finite energy connection on R4. Then since it's a four-dimensional solution, I'm going to just be annoying and call it B also, right? It's also a bubble. So A equals B. So our original connection A is also a bubble solution. Now, remember what we did to get our sequence over here, right? We took a sequence of dilations, and we pulled our, sort of down our connection A by it, right? We were pushing it into smaller and smaller balls so that it would limit to some trivial connection A naught over here, with the property that if we looked at what happened to the energy measures of this connection, then what we computed was that it was 0 plus a Dirac delta at this point, right? So our defect measure in this case, right, is just this. There's our, oh, good, I have it right. There's our mu, right? The support of mu is just the origin, right? So if I were to pick a point in the support of mu to find a bubble, I don't have many choices. Now, note the following trivial thing. So if I were to take the support and if I were to look at our AR, then I could blow it up by R, right? And what happened? In fact, I mean, by definition of how I got AR, I just get back to A again, right? But certainly that converges to something, right? In fact, it's constant, it's stupid, and it converges to B, right? So what we're saying here is that our B, which was the same as our original A, is actually the unique bubble at 0 this way, right? So bubbling phenomena here was basically a canonical way of re-blowing up what we were blowing down in this example, right? It was a way of recapturing our original A inside of our sequence. And let me sort of emphasize a few points of this because this will be important now. So let's now reevaluate the defect measure mu in this example, right? So over here, when we took our limits and our supports and we had our defect measure here, for our defect measure, again, just to rewrite A as B, what we actually had was that the 0 Dirac delta at 0, and that was actually equal to the integral of the energy of the bubble at that point times the Dirac delta, right? So the multiple of the Dirac delta you got in front wasn't some random something. It was precisely the energy of the unique bubble you got at that point, and that turns out not to be a coincidence. Yo.
Is that solution in R4? Is that the only solution up to dilation center at 0?
There are lots of solutions. No, there are lots of bubbles.
So there could be other bubbles.
Whole bunch. Yeah, whole bunch. Right. I mean, in principle, you're asking if the original A here is the only global R4 solution. Is that what you're asking? Yeah, up to dilation and translate. Yeah. No. It is somehow the simplest one, right? Everything else basically has more energy than this one. I've basically given you the smallest energy example is what I've done. But there are lots of guys that have higher energies than this. They're basically, you can sort of imagine actually taking like two of these guys and trying to glue them together far away, right? Because they don't really see each other if they're both in neighborhoods. Right? So you can do this in lots more ways. Right? And actually, exactly on that note, in principle, right, at a defect measure, you may not have one bubble, you may have a whole bunch. There may be bubbles on bubbles, a whole bunch of mess can occur. Different sequences Ri going to 0 with different Xi going there can get different bubbles out of this. But in this example, we get this. Okay. So the energy identity, which you might start to guess at this point, is supposed to be the following, right? So let's make an observation first. Take some point in the support defect measure here. Right? Let's look at a whole bunch of, I'm going to call distinct bubbles at that point, and I'm not defining for you what distinct means. So take a whole bunch of distinct bubbles at this point. Then one can actually fairly easily prove the following. So the energy density at this point here should be at least the sum up to this, the volume of the n-4 ball factor, should be at least the sum of the energies of all these bubbles that you actually got out from here. So intuitively, why should that be true? It's because every time you have a bubble, right, this bubble here was basically a solution that was getting pinched off at this point and disappearing in the limit. Therefore, one expects the energy of this bubble to also disappear in that limit. Right? So you can show that the energy density at this point should be at least the size of all these bubbles, right? Each one of these contributes some amount of energy you've lost in that limit. And as you might guess, the energy identity is the picture that is the conjecture that that's it. It should be equality, right? So more precisely, the energy identity is the claim that you can find some distinct bubbles, right? So you got to be careful. Maybe you missed one, right? But there are some number of distinct bubbles so that you have equality. So the energy density at that point is exactly the sum of the bubble energies. So the amount you lose somewhere, you can exactly compute through these trivial solutions, four-dimensional solutions. Four-dimensional solutions are responsible for all energy loss, in some sense, in the limit, regardless of your dimension. It's just the four-dimensional trivial guys that contribute to the energy loss. Okay. Oh, one more example. Okay. So. Oh, good. Example. Excellent. So this is an easy example, just to see this in practice in higher dimensions. Oh, I'm not going to have enough time to get there anyway. I won't worry about drawing a picture. So again, as always, let's start with our four-dimensional global solution on R4. And I'm going to build for you some sort of example of bubbling and all the rest of this in higher dimensions. And the place you should start here is just the dumb thing. So I want to take my sequence AR on R4 with their energies. This is all we've covered. Right. And now I want to view them so I want to view these solutions AR as being solutions on R5 by ignoring the last variable, right? So I'm crossing by R and just letting them really just be solutions on the four-dimensional slice. So then what's kind of happening here, here's our sort of L is our R5 axis, right? Here's our four-dimensional variables. So our curvature concentration now is more like this, right? Along the slice, but then in the same game where now it starts to pile up. So if you were to take your sequence and your limits, once again, you'll limit to a trivial connection because away from L now, away from this one-dimensional line, you have that the connection is actually the curvature is going to zero everywhere. So you still limit to zero, but your defect measure in this case now becomes a Dirac delta on the line, right? So you have your not a point, but a codimension 4 manifold, right? Your single line that actually appears as your defect measure. Everything got crossed by R, so therefore your Dirac delta is crossed by R too. And of course, you can play the exact same game because nothing's changed, right? There's a unique bubble at each point. It's A itself. And this, again, is sort of illustrating the energy identity in higher dimensions. I actually lied here. There should be a volume of the ball of radius 1 in front of this because you're, right? I mean, you actually look at a ball here, right? Which means you see this little piece when you do your dilation. Okay. So there's our simplest example in higher dimensions, so we can see what's happening. Okay, so just to sort of relate some progress. So before I state that sort of main theorems, now let me sort of mention what was sort of done before. I have to explain a word here. So this energy identity, I mean, this first came up in moduli space theory. It was proof for four-dimensional instantons by Taubes and Uhlenbeck. So just to use the word instanton for a second, how do you explain this? So we spent a lot of time, right, understanding Yang-Mills as being harmonic connections, right? So it's like a second-order equation that it solves. So what's better than a harmonic function, right? What's better than a harmonic function is a holomorphic function, right? They are harmonic, right? By just squaring the Cauchy-Riemann equation, but they're better. They still have a first order equation, right? That's what an instanton is. It's a first order equation that is sort of more related to holomorphic than it is to harmonic, right? So it's stronger than Yang-Mills. The reason things are so much easier for instantons in dimension 4 is that you can basically relate energies to topological things. So proving things like energy identity actually becomes pretty easy. You just have to sum some topologies up and see what's happening. It was proved for instantons in general dimension. This means mainly complex manifolds, but you can actually do this in other contexts by Tian. And the first time sort of a general stationary case was proved was by Tristan Riviera. So he proved in dimension 4 that for any old sequence of Yang-Mills, you actually do have your energy identity in this case. And what he also proved at the time was he did actually tackle something about higher dimensions, and this is going to start relating us to a priori estimates now. What he proved was that if you have your sequence AI of connections, and if you assume that besides having bounded energy, of course, that their Hessians have uniform bounds in L1, right? This is somehow it's somehow something one might expect to be true, but is certainly an assumption. Then he proved the energy identity in this case, right? So he actually proved that L1 Hessian bound improves energy identity. It's a really neat proof, by the way. Let me tell you like 3 things about it because you should Google these things. So we've all learned Sobolev embedding, yes? Turns out Sobolev embedding is weaker than it has to be. So it's true that W1P embeds into some LQ spaces. It actually turns out it embeds into something stronger called an Ornstein-Uhlenbeck, right? Ornstein-Uhlenbeck, that's an operator. To an Ornstein. Lorentz, thank you very much. Too many names in my head. Into a Lorentz space. Not of the Minkowski variety, right? This is a different thing. So it embeds into a Lorentz space. Being in an LPQ space, that's what Lorentz space, this is weaker than being in like LP plus epsilon, right? So you can't push up the P there, of course, in Sobolev, but it is stronger than LP. And they were able to use this to actually get that teeny little bit of extra control to actually get the energy identity out of it. You're going to find in your careers that the hard problems always come down to getting the teeny little bit more, right? Once you get that teeny little bit more, you can actually turn to a lot more pretty easily, right? It's always about finding the smallest, weakest possible thing that you can get away with. Okay, that's what he proved. Right, okay, so main results. Just to be annoying, just to sort of, again, you can view all this as being an Rn with trivial connections. I don't care. The whole point being is that actually you can be on any old manifold as long as it has some C2 bounds on the geometry. It's pretty irrelevant. Even the manifolds converge in this, but think Euclidean space. Doesn't matter. So take a sequence of stationary solutions, let them converge out so that you get your defect measure. And of course, the theorem here I'm going to say is that energy identity is true, right? So you can find a sequence of distinct bubbles so that the energy at almost every point of the support is actually equal to the sum of the bubble energies. And our wrong way. And our second result is to prove the L1 Hessian bound. Right, so automatically, if you have a stationary Yang-Mills connection, it simply holds that the Hessian of the curvature has an L1 bound. L1 bounds are notoriously painful to prove. All right, it's a badly behaved Banach space, right? So these things tend to not be so well adapted to elliptic equations so often. And as I mentioned in the beginning, what we don't do is prove this first and then use Tristan's result. We actually have to prove both at the same time, as it turns out. They kind of both come from the same. They're very, very different techniques, which sort of just produce both. Beep, beep, beep. Oh yeah, and another point I should mention, because this is sort of becoming the fad, so it seems. We don't talk about sequences so much. Basically, in the end, we apply it to a sequence, but everything's quantitative in my world. Everything is proof for a fixed single solution. It's just better that way. Not just as a statement, I mean just to think and work that way, I mean. So we really have a quantitative version of this energy identity, which gets proved, and it actually holds for any solution. And basically by applying it to sequences, you end up with this. I'll try to explain it a little bit. Okay. So broad strokes, which basically means I'm going to go through this example again to see why it's true in a more quantitative sense, right? So let's point out some more special behavior about this sequence of solutions here that might lead one to how you might try to approach this. Running out of space. Okay, so I'm going to fix some small number delta now because we're analysts and we like deltas. So remember our sequence over here was the sequence of blowdowns, and they were converging to this Dirac delta, and the curvature was going to 0 away from the origin, right? So now let's observe the following. So fix some really small delta. Any delta you really want, just make it sufficiently small. Now, what I really want to do now is I'm going to take one of these solutions. So let's just pick this guy, for instance. No, that's way too. Pinch it a little bit more. Okay, better. There's this. Here's our R. AR here, right? So let's take one of these solutions, and I want to break it up into two pieces. Right? One piece is basically roughly just this ball of radius R here, except because we're analysts, I'm going to be annoying and make it delta inverse times R, right? So I'm out here. I didn't actually write this. I put 2 in front of there, I put 2 in front of there, so they'd overlap. Okay. So let's let this region here, which is basically just a ball of radius R, be we'll call it beta. Squiggly b, Greek b, whatever you want. And let's let A just basically be everything else, right? So I'm going to let A be, keep in mind this is actually a connected region, right? This is R4, not R1, right? So A is going to basically be everything here. And if I want to, actually, it should be better to call these things like AR and B, squiggly AR and squiggly BR. Just signify that they're for this connection here, right? So for every single R, I can do this, but this is a different decomposition for each R, of course. So let me make some observations about this really stupid way of breaking things up, right? There's nothing remotely clever about that, right? It is the natural thing to do. So some properties. In particular, these are properties that are, with delta fixed, independent of R about this. Brilliant property number 1, there's always two pieces. So no matter what R is, I've broken up this solution into two pieces, right? There is an actual important moral there, right? The idea being is that, as R gets small, you're basically having blow up, right? Things are going really bad. But regardless of things going really bad, I've broken this thing up into a bounded number of pieces regardless of how bad it is, right? In the example, it's sort of clear how to do that, right? So no matter how degenerate it is, it's two pieces to this decomposition. Point number 2. So what do we know about this sort of what we're going to call an annular region here? So once we move, some amount away from our bubble, the curvature is small, right? By small, of course, we mean scale invariantly small, right? So it's always scale invariantly small, and in fact, it's not such a hard computation. Remember, the curvature is decaying on R to the 4th rate here, to see that the curvature squared, the energy on just these annular pieces here, is itself really small, depending on no, it's not going to 0 as R goes to 0, right? It's just small with some fixed delta, right? No matter what R is here, it's actually basically the same, right? But some small something, if my delta is small. Believe it or not, in the general case, this is the highly non-trivial point right there. That's what's going to become, just such a disastrous pain to prove. And the third point is that if we look at any of our bubble regions, B, these guys here, then the ball of radius R here, right, there's some definite amount of energy here, right, on the one hand. So most of the energy is contained in here. This is basically the same statement as saying most of the energy is not contained in here, which was the last statement, right? And on the other hand, again, basically the same as the fact that this has very little energy. If we look at the energy of the entire ball, right, most of it is inside this region here, right? Again, independent of R. Even as things start to sort of degenerate and you blow up here, most everything is inside this single one region, right? Okay. So I'm going to call these, roughly speaking, delta annular and delta bubble regions. And what I basically want to sort of roughly outline is how one might mimic this in a general scenario. Right? This is kind of roughly what you want to say. An arbitrary random solution satisfies these properties, more or less. That's kind of what you want to say. Oh yeah, and no, this is basically like a quantitative energy identity, right? We've said that for any small delta we want fixed, we split it up into just two regions, and one of these regions is like a bubble region, one of them is like an annular region, and most of that energy is in that bubble region, right? So one can view this as like a quantitative version of the energy identity if you want, for a fixed solution, right? No sequence is really necessary. Okay, so now let me try to, say in some vagary what this, actually, I think I'm like halfway through my slides. So let me try to say, again, in some general words, what the general situation looks like. Then I'm going to show you what I'm going to skip to. I'm going to skip everything and just kind of go straight to what the gauge is, because this is sort of an interesting point, I think. And we'll end on that point. So three basic points here. So quantitative tree decomposition is basically that right there, right? So it's, you've got this. So in general, what you're going to do is decompose a completely random solution, right? You're just handed a solution with bounded energy, you know nothing else about it, and to some regions. And the delta bubble regions will in fact look like this. They will basically look like four-dimensional solutions. That's going to be true. And the delta annular regions are basically going to be regions that actually look flat if you're kind of staring at it in some sort of fuzzy sense, right? The curvature is very small. So when you're staring at this guy for very small, the curvature is all here. Fuzzily, your connection looks flat, right? I mean, that's the statement that it limited to the flat guy, right? So annular regions are flat regions, and the delta bubble regions are like four-dimensional solutions. And it turns out it is true that you can split up your random solution into just those guys. What I should point out here is that, so in dimension 4, what you'll say is that no matter what, you can't tell how big or small these balls are, right? These annular bubble regions, like in these examples here, right? As things blow up, the bubble regions get smaller and smaller and disappear in a limit. But in dimension 4, there's always a finite number of them no matter what. No matter how they're scattered around, there's a finite number of them. And what finite means in higher dimensions is, n minus 4 finite in higher dimensions. And what that means is n minus 4 content bounds. Right? That's the correct way of saying n minus 4 finiteness for a covering in higher dimensions. The majority of the work is into actually proving these annular regions in higher dimensions that look kind of like that basically satisfy exactly the properties we just wrote down for these guys. Namely that their energy is actually small, right? And if you want, actually, their L1 Hessian is also small. So that this is the majority of the work. And the other thing you have to do is prove the same results in the bubble regions. That actually turns out to be easy. That's almost by definition. That turns out to be kind of trivial from the definition of a bubble region, which I'm not going to give. The main reason being is that if you want a quantitative bubble region, one can say it easily. It looks, smooth, close to a four-dimensional solution. That's true. The problem, of course, is that in principle, one has bubbles on bubbles on bubbles, which means that when you actually say it precisely, you've got to take this into account, and you really want to hit your head against a wall, and I'm going to spare you. But roughly, it's smoothly close to a four-dimensional solution. And therefore, that should be trivial. Okay. So Now, let me sort of break this up into two pieces. What I would like to do, how much time is left? We have 10 minutes, let's say. Oh, I got 15. I'd like to define for you what an annular region looks like in higher dimensions. I think I won't. I don't think after this much time you're going to follow what I say, unfortunately. It is a very useful notion. It's something that these sorts of annular regions or neck regions have become quite important in stratification theory. I mean, they were used in the proof of L2 curvature bounds for Einstein manifolds, and the proof of rectifiability of the singular sets and so forth and so on. They are the right way to break stuff up, but they are a handful when you look at it. Somehow it's one of those things where after 15 minutes you kind of realize, oh, that's the only reasonable way to write it down. But it takes 15 minutes to get to that point. So I'm going to skip it and just kind of talk about the epsilon gauges. So let me... Okay. Skip ahead. So let me make a few comments about epsilon gauges. And actually, so now that, since I've skipped all the annular stuff, what that means is that for my last 10 minutes, I'm basically kind of starting over to a certain extent. So if you've fallen asleep, it's a reasonable time to wake up. Okay, so of course, as we spent the last basically 2 days before this discussing, a key notion is that of a gauge, right? So our connection, when we talk about regularity of our connection, it doesn't really make sense because you can write things in different coordinate charts. So when you say regularity of a connection, what you really mean is how good of a coordinate chart can you pick to make it look so nice in, right? And when you're trying to answer this question, you try to answer what's the best coordinates to write things in. And the conclusion we came to over the last few days were Coulomb gauges, right? This is where everything was sort of written. Now, the issue with this is kind of the following. So I've been sort of slicing my dimension 4 here. I'm going to plane it instead. So instead of treating R4 like R1, I'm going to treat it like R2 here. So for the Coulomb gauge, right, remember what we needed was let's say a delta flat ball, right? We wanted a region where the curvature was small on the entire ball. And if the curvature was small on the whole ball, we had these nice Coulomb gauges that actually existed on the ball of radius 1, and we were happy and we were good and we could prove everything we want to prove. The problem with annular regions is that, so what's happening for R very small here is that, your curvature is basically all right here, right? It's all kind of concentrating at this point. Now, that means that when you look at it in some fuzzy sense, it looks like it's very flat, right? It looks just like a flat region in some sense if you don't stare too hard. But there's a huge curvature bubble there, and that causes all kinds of problems. So one of which being that Coulomb gauges may not exist. If they do exist, what is absolutely for sure is nice ones do not. So I mean, remember part of our existence of a Coulomb gauge was that we wanted the connection A to actually be small inside that Coulomb gauge. That was part of our point. Those actually simply do not exist. You can prove for topological reasons they do not exist in a ball like this. So you're left with a problem of how does one actually do analysis over that guy, right? I mean, when you want to write things in Coulomb gauges, but you can't write things in good Coulomb gauges. So, right, because we like it when things solve equations. So what we're going to do instead is the following, and how much do I babble inside this? I think I just said all that, so let me skip it. So there are a couple of ways of trying to fix this, right? Just to sort of lead us up to an answer, right? So if we have one of these annular regions, so like this in the 4-dimensional case, it's very simple, right? This was basically literally an annulus in dimension 4, right? So in dimension 4, it was nothing more than just sort of, the region between where your bubble kind of was appearing and 1, right? So annular regions in dimension 4 are super simple. They really are. They're just annuluses. And they were annuluses for which you looked very flat in this region. So the two things you might try to do is, one, you might try to find a Coulomb gauge in just this annulus, right? Ignore what's happening inside. So one can actually probably do that, I imagine. The problem is that it somehow defeats the purpose, right? If I hand you a harmonic function that's harmonic away from a small ball inside, regularity theory fails. So what? So this is not that helpful of a thing to do, as it turns out. Trying to build this. You want something that solves an equation over the whole thing is the problem. So you can ignore that ball, but that doesn't help. And in higher dimensions, it's not even clear, you can even do this, by the way. In dimension 4, I think you probably could. And regardless, actually, I should say, in dimension 4 you can, but it's kind of after the fact. So that what that means is that you prove a huge number of estimates first, right? So this is actually done in dimension 4. You prove a huge number of estimates first, and you use those estimates to prove the existence of the gauge. That defeats the point. The point is to use the gauge to prove estimates, not to use estimates to prove the gauge. So just said that. So instead, what I'm going to do is the following. We're going to basically linearize the Coulomb gauge condition. So we've got this vector bundle sitting over this whole ball, right? And this vector bundle is equipped with a metric connection. And that means, in particular, I can make sense of things like harmonic vectors, harmonic sections of this with respect to that connection, right? If you actually think for a little bit, this is like a linearization of the Coulomb gauge condition a little bit. So what we're going to do instead is solve for a global harmonic coordinate chart here, right? As sections of our bundle on all of A. So let me be a little bit more precise about what that is. So the definition is the following. So let me give a definition first and discuss it after. So we say, so this is so the fibers are k-dimensional, right? This is just like, let's say the ball radius 2 cross RK, who cares? So we say k sections of this bundle, right, k vector fields, form a harmonic epsilon gauge if the following hold. 1, they are harmonic with respect to your Yang-Mills metric connection. Right? 2, and basically in L1 sense, they're almost orthonormal. Right? So if these things were somehow, if this is a metric bundle, right? So if this was a real gauge, these things should actually be an orthonormal basis. And what you're saying is that in an L1 sense, they're close to being an orthonormal basis. Note, this is a horrible thing. It basically means there's a big giant hole here where you know nothing, right? So on some large set of measure, these things are close to being a basis, but you know nothing else a priori. And the third thing you say, so if this were a flat ball with a flat connection, what could you do? The canonical trivialization would have this is actually 0, right? And it would have that the gradient is 0, because if you had a flat connection, it should be a parallel translation invariant section. You can't do that, but you can, in fact, insist that it be small in an L2 sense. You can actually prove small in L4, but that's harder, and it's easier to produce these guys off the hand. So that's it. That's a harmonic epsilon gauge. Now let me make a few comments about this. So first off, if this happened to be a flat ball, not kind of weakly flat the way that is, these things would automatically, this would automatically hold pointwise, and this would automatically hold pointwise. So it would actually be an honest vector bundle gauge over the whole thing. Right? So that would be true over a flat region. So somehow, in the context of how we've talked the last 2 days, we could have worked with these guys instead. It would have been just as good. Not as classical, but just as good, right? Number 2, again, for topological reasons, it turns out, these guys cannot, in the case where you actually have concentration here, form a global vector bundle gauge. It can't happen. There will be zeros of those vector fields inside here somewhere, right? So these things solve something globally, but in some sense they stop being an actual gauge at some point in the bubble region. What you end up being able to prove, and this is in some sense 90% of the work, is that they automatically form a gauge on the entire annular region. So at least where it is that you want to use them, because that's where we're trying to study, they will for free be an actual, almost orthonormal gauge on the whole thing. That's for free. So it's not a real gauge, but it is on the annular region, and they do solve something over the bubble region, right? So they sort of have a little bit of both worlds going on from that point of view. Okay, and I won't really say how, but the point is one can actually do analysis with these things. And eventually what you do is you turn curvature estimates into estimates on these guys, prove estimates on those guys, turn them back into curvature estimates, and then you're done. More or less. Oh, let me point out one thing for you, just so you see it. Why is Yang-Mills important in this nonsense? It turns out it's in this equation here. So you know, what's nice about you know, harmonic functions in Rn? You can compute something called a Botner formula, right? You compute that the Laplacian of the gradient of u squared, if it was a harmonic function, is just the Hessian of u squared. Right? If you're on a random bundle, you end up getting extra terms. You get a curvature term, and in principle, you get a divergence of the curvature term over here as well. And if you're Yang-Mills, that disappears. And that ends up being why you can control these things, actually, is that this is actually not such a bad equation. The divergence term is actually the really bad term, and you can kill it. Okay, so to say that was rough is, you know, a minor exaggeration, but we'll keep it and stop. Thank you. Yo.
About the energy identity for critical points of the Yang-Mills, for weak Yang-Mills as opposed to the stationary.
Oh, in that case, I would imagine you can find weak Yang-Mills solutions for which, you know, you are probably nowhere smooth, right? I mean, you can do this for harmonic maps, so I would imagine you can do it for Yang-Mills as well. So in some sense, the question's even ill-defined.